Hello. This is lecture for real zeros of polynomials. That's section 3.5 in our textbook. All right, let's begin with a quick review of what the zeros of a polynomial are. If we have the graph of a polynomial, let's just put one on here. Say this is a polynomial. The zeros of that polynomial are going to occur where that graph intersects the horizontal axis, right? So we might call the real zeros horizontal intercepts. All right, so how do we go about finding the zeros of a polynomial? Well, if we have a nice graphing utility, we can usually find them by playing around with our window. But what if we have a strange polynomial that makes it difficult to find the zeros? Or what if we don't have a graphing utility? Well, Cauchy's bound is a mathematical, or I should say an algebraic way of finding the zeros of a polynomial, right? So if we place a polynomial in descending order of the exponent, right, that's kind of a standard form for polynomials, right? Then the leading term will have the coefficient a sub n. Okay, of course, a sub 0 is your constant, and all the other coefficients of the terms will be a sub 1, a sub 2, a sub 3, etc. All right, so if we let m be the largest coefficient in its absolute value, so we don't care about the sign on it, we just want the largest absolute value coefficient, then we can establish an interval within which all the zeros of the polynomial will lie. And that interval will be negative m, again, that's the absolute value of the largest coefficient, divided by the absolute value of a sub n, right? That's the leading term, the coefficient of the leading term. Should have written that all the way out, coefficient of the leading term. Okay, it'd be negative m divided by the absolute value of a sub n minus 1. That's going to be the lower boundary of the interval. The upper boundary would be m over the absolute value of a sub n plus 1. All right, let's take a look at an example using Cauchy's bound. So if we have the polynomial f of x equals x cubed plus 4x squared minus 11x plus 6, okay, let's see if we can find the interval within which all the zeros of f of x will be, right? Or the interval that contains all the real zeros of f. Okay, we're only going to deal with real zeros in this section. We'll talk about complex zeros or imaginary zeros involving imaginary numbers in the next section. All right, so Cauchy's bound said that these would lie in this interval. It's going to be negative m over the absolute value of a sub n minus 1, and then m over the absolute value of a sub n plus 1. There's our interval. So what is m here? M, that's going to be the largest the largest coefficient, right, in its absolute value. So we have coefficients of 1, 4, negative 11, and 6. The largest is going to be 11. All right, and then what would a sub n be, or the leading coefficient? Well, the term with the largest exponent is x cubed. The leading coefficient of x cubed, of course, is just 1. All right, so that means the interval that would contain all the real zeros of this function f is going to be negative 11 over 1 minus 1 to 11 over 1 plus 1, or we would say that's negative 12 to positive 12. All right. That's how we would go about finding that interval. So the interval that contains all the real zeros is helpful in finding them, but how do we actually go about finding what those zeros are? Well, we have another theorem called the rational roots theorem. The rational roots theorem finds all the possible real zeros, all the possible real zeros of a polynomial, right? So again, if we have a polynomial in its standard form, a sub n times x sub n plus a sub n minus 1 times x sub n minus 1 all the way down to a sub 1 x to the first power plus a sub 0, the constant term, okay? If it has integer coefficients, then we can say that r is a rational zero of that function. Then r would be take the form plus or minus p over q, where p is a factor of the constant term, right? So p are factors of the constant term, right? And q are factors of the leading coefficient. Right? So in other words, if we want to find all of our zeros, we need to first find all the factors of the leading coefficient and all the factors of the constant term. All right, let's take a look at an example. Okay, here we have a polynomial, f of x equal to x cubed plus 4x squared minus 11x plus 6. Okay, we're going to use this rational roots theorem to make a list of the possible zeros of that, the possible real zeros of that polynomial. All right, then we'll go ahead and use long division to find the zeros. Okay, so what are they? First, we need to know what p and q are, right? So recall, p we said were factors of the constant term. All right, let's go ahead and find factors of the constant term. The constant term is 6, right? So what are its factors going to be? Well, let's see, 1 times 6 and 2 times 3. I think those are all the factors, so we could say plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. These are all the factors of 6, right? Then we'll need to know all the factors of the leading term, right? Well, there aren't any there. It's just going to be, those factors are simply going to be just plus or minus 1, right? Since we don't really have any. So all of our rational roots here, all of our possible, I should say, rational roots, real roots, are going to occur at plus or minus p over q. So let's see what those are going to be. So the p over q's, let's do it like this, plus or minus p over q's are going to be, see, these guys were all our p's. So we can say it's going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, of course, just 3, right? And then plus or minus 6 over 1, of course, that's just 6. So these are all our possible roots. How do I know which ones they are? Well, I could test them all with long division, and that's the only way I'm going to know for sure, right? We know that if the remainder is 0, then that divisor will be a root of the polynomial from previous sections, right? The remainder theorem and the factor theorem. Okay, well, to spare you all watching me do a whole bunch of calculations, I'm going to go ahead and here's what I usually do. I usually graph it and look for the ones that are most likely. Okay, look for the ones that are most likely. All right, so let's see. Maybe 1 is going to be, positive 1 is going to be a root. If positive 1 is a root, that means that x minus 1 is a factor, right? X minus 1 is a factor. So let's just make sure, we'll do long division here to see if x minus 1 evenly divides into x cubed plus 4x squared minus 11x plus 6. All right, x goes into x cubed, x squared times. So x times x squared is x cubed. X squared times negative 1 is minus x squared. Let's subtract that out. All right, so then we have 4x squared plus another x squared, so that'll be 5x squared. Okay, bring down that negative 11x. Okay, x goes into 5x squared 5x times. All right, let's multiply that out. 5x times x, of course, is 5x squared. 5x times negative 1, of course, is negative 5x. Let's subtract that out. I have to continue up here. We're running out of room here. 11x plus 5x, I'm sorry, negative 11x plus 5x is negative 6x. We would bring down that 6. Put it over there. All right. And then x goes into negative 6x, negative 6 times. Okay, so then we multiply that back out. We get negative 6x plus 6. And of course, when we subtract that out, we have a remainder of 0. All right, so that proves that x minus 1 is a factor. And again, before the days of graphing calculators, or if you didn't have a graphing calculator, you would have to try every single plus or minus p over q. You'd have to try positive 1, negative 1, positive 2, negative 2, so on and so forth. You'd have to try them all to see which ones had a remainder of 0. We aren't going to do that, so we do have technology available to us. All right. Of course, sometimes we have to do this because our graphing calculator can't give us an exact 0 when it isn't a whole number, when it isn't some readily determined decimal. Sometimes we have roots that are repeating decimals, right? And so writing them in their fraction form is really the only way to get the exact answer, and that's where we would have to use the rational roots theorem. All right, so what did we did that long division. What did we have left? Well, we had x minus 1 times x squared plus 5x minus 6. All right. Now I could try and find another factor and do long division, but I know with a quadratic, if there's a root, it's going to factor. All right, it's going to factor. So if x squared plus 5x minus 6 is going to factor, I can do that. That's a little easier than long division, I think, and guessing and trying to find the one. So let's see what that'll factor into. X squared plus 5x minus 6 is going to factor into x plus 6 times x minus 1. All right, so there we have all the factors of that polynomial written out. So now I can be sure what all the zeros are. So what are the zeros here? The real zeros. The real zeros are going to be, let's write them in descending order. How about negative 6, positive 1, and positive 3? Okay. Let's take a look at B. All right, let's start by finding Cauchy's bound for that, so we know where the real zeros, the interval within the real zeros will lie. All right, so remember, Cauchy's bound, we need to know what? We need to know m and then the leading coefficient, right? M, the largest term here is 49, all right? So my boundary here is going to be 49 over, negative 49 over the leading term in absolute value 2. So it's going to be negative 49 halves minus 1 up to positive 49 halves plus 1. There's my bound. Let's just simplify that. Let's see. That's negative 24.5 minus 1, or negative 25.5 up to positive 25.5. So there's the bound, or the interval, within which all the zeros will lie. They will all occur in that interval. Now, how do I find out what they are? Let's try this plus or minus p over q thing. All right. So what are all the plus or minus p over q's? Well, what are the p's? First, we'll need to find our factors of 20 for the p's, right? There's quite a few for that. So we'll have a plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Okay, q here is negative 2. All right, what are all the factors there? Just plus or minus 1 and plus or minus 2. All right, so what are all my P over Q's? Well, let's see. I can have plus or minus 1 over 1. Right? Then I can have plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 5 over 1, plus or minus 10 over 1, plus or minus 20 over 1. Then I can have plus or minus 1 over 2. Plus or minus 2 over 2 is 1 over 1. I already have that. 4 over 2 is 2. I already have that. There's plus or minus 2. Okay, then I can have plus or minus 5 over 2. 5 halves. Plus or minus 10 halves is just plus or minus 5. We already have that. And then plus or minus 20 halves is plus or minus 10. So we already have that. So wow, here's a whole lot of possible zeros. A whole lot of possible zeros. Okay. Now again, we'd have to test each. We'd have to test each one with long division before we had graphing calculators. But now that we do have graphing calculators, we're not going to do that. You know, I would go ahead and graph this. And when I graphed it, I would find one clear point anyway and use long division to find the others, right? Use long division to find the others, to find the other factors. All right, so let's see. When I do graph this, one zero that's pretty clear is positive 4. One of them is positive 4, which would mean that x minus 4 is going to be a factor. All right. So if we do long division into our function here, negative 2x cubed plus 9x squared minus 49x plus 20, if I do long division in there, then I will find what's left, and I could try one of the other factors. Now let's see if I can we'll just open a blank page here. There we go. I don't really want that. Let's see if we can just make that go away. There we go. And let's make that go away too. There, now just a blank page. All right, so we saw from graphing it that 4 was one of the zeros. Looked like it anyway. We're going to test that. We're going to divide it out just to make sure. All right, so if 4 is one of the zeros, positive 4, that means x minus 4 should divide evenly into our polynomial. It should divide evenly into our x cubed, let's see, what was it? X cubed plus 4x squared. Look, I've forgotten it. X cubed plus, I'm not doing the right one. Let's do it over here. So x minus 4 should divide evenly. Let's just start all over here. I don't know how to, I haven't learned how to erase from here yet, so I'll get there, I guess. All right, x minus 4, if that divides evenly into, here's my, it's negative 2x cubed plus 19x squared minus 49x, then plus 20. Now I have the right polynomial. All right, x goes into negative 2x cubed, negative 2x squared times. Let's put that up there. All right, we'll multiply that out. We'll have negative 2x cubed, negative 2x squared times negative 4 would be positive 8x squared. All right, so we want to subtract that out. 19x squared minus 8x squared is going to be 11x squared. Okay, we'll bring down that negative 49x. Okay, x goes into 11x squared, 11x times. All right, Multiply that out, we get 11x squared minus 44x. Okay, we'll subtract that away, and we're left with a negative 5x. Bring down that 20. X goes into negative 5x negative 5 times. All right, so when we multiply that out, we get negative 5x plus 20, and subtracting it, we see that there is no remainder, so that just proves that 4 is, in fact, a 0. It is, in fact, a 0 of the function. All right, so what do we could write our function now in factored form. We have x minus 4 times, what's left, negative 2x squared plus 11x minus 5. All right, and then we could, usually when we get down to a quadratic, we like to see if it'll factor or to use the quadratic formula. Yeah, this one does factor, or I could use the quadratic formula to find the remaining zeros. When we factor it, what do we have? 2x minus 1, which, I'll just write it this way. 2x minus 1 times x minus 5. All right, so the 0 that x minus 4 leads to is 4. That's the one we saw from the graphing calculator. The 0 that x minus 5 leads us to is 5. Okay, so that's one of the zeros. What 0 does the 2x minus 1 lead us to? Well, with the zero product principle, we set it equal to 0 and solve. So 2x is 1, and we divide by 2x is 1/2. And there's our third 0. Right? So to summarize, Cauchy's bound is how we can find the interval within which all the zeros, all the real zeros of a polynomial function will lie. Right? Then we can use the rational roots theorem to find all the possible zeros. Using the rational roots theorem, we need to find all the factors of the constant term, divided by all the possible factors of the leading coefficient. And that gives us all the possible zeros. I will ask you to know both of those in a testing scenario, so make sure you're comfortable with that. But then what I recommend you doing is graphing it on your graphing calculator. See if you've got a whole number or a very clear 0. If you've got a clear 0, test it using long division, like we did here. Test it using long division. And if you have a remainder of 0, then you can be sure that that was a 0 of the polynomial. Okay, and continue in that manner to find the remaining zeros. Usually when I get down to a quadratic expression, then I see if I can factor that, or I might use the quadratic formula to find those last 2 remaining zeros. All right, this ends the lecture for section 3.5.